Hi guys. In this part, we are going to consider the part 4 of the lecture, in which we are going to look at how TNNs can be used to model sequential data. So far, we have seen recurrent architectures, such as recurrent neural networks or LSTMs, which have the following properties. They allow you to handle arbitrarily long sequences because due to this recurrence, they can be sort of controlled for arbitrarily many steps, and that allows them, in principle, to handle arbitrarily long input sequences, and they can theoretically learn from the arbitrarily far past, right? But a problem that they have is that they suffer from this vanishing and exploding gradient problems explained before, which means that actually learning in practice from the far past is a very difficult problem. What we are going to see now is that these CNNs applied to sequential data are actually a very interesting alternative to these recurrent architectures. And we saw in lecture 3, if you remember, that this convolutional 1D operation can be used for time series. So if we want to calculate the answer for the value depicted here by present, we would just put some sort of kernel, convolutional kernel, center around that point, and we would do some sort of dot product, and that would give us the convolution, right? Then we would just shift it everywhere, and that would give us the response of the convolution operation. But there is a catch here, and is that this standard convolution formulation considers values from the future while we are considering while we are computing the value of the present. So when we put it in the center around the position theta we want to compute, for example, then we have some values that are in the past and also some values that are in the future, that is illustrated here. And this is a inconveniency for multiple tasks, such as sequential sampling. Imagine that you have a task in which you want to produce text, let's say in real time or something like that. Then you don't have, you cannot really observe the future and able to get to the value that you want to put out in the present, right? So this means that we need to provide convolutions to something called causality. That is a property in which the output at a certain position is only dependent on the input at that position and positions before that, which means we are not observing positions from the future. And we need to provide then a causal formulation to convolutions so that they behave that way. So if we have a convolution normally that would look like this, what we would like now to have is a convolution operation that now looks like this. That is, there is no connection to the future, which means that we have this causality property. And how this is done in practice is actually quite simple. The only thing that we need to do is consider padding asymmetrically. So normally when you have a sequence, you put padding at both sides in the same way, right? As shown here. What we need to do in order to obtain this causality property is just go and put all of the padding at the beginning of the sequence instead of center, instead of on both sides. And for example, if we have a kernel size 3, then the one thing that we require is to have a padding of k minus 1 at the beginning, and then we achieve this causality property. So for example, here, if we have a kernel size 3, and we put it here, it's just going to be depending on the position 0. If we then shift it once here, then it's going to be depending on position 1 and 0. And if we continue in that way, it is always going to be limited by the position which we are calculating the computation for. And that's different from this normal padding that you have here, for example, because here, when you are computing the value for the position 0, you would also be looking directly at position 1 as well. So that means that via this padding, we obtain exactly the causal formulation that we want to obtain. And this is how you do it. So now the following question that arises is regarding the receptive field of the convolution. And in particular, the receptive field stands for the elements on the sequence that the convolution is actually able to observe when it's computing the convolutional operation. So if you have a convolutional kernel as k, you are able to observe k minus 1 steps in the path, and that determines what kind of functions you can make, right? So here, for example, we have filter that is of size 2. So the amount of positions in the path that we are able to observe is equal to 1, right? So now the question that arises is how to deal with long-range dependencies. And this is, of course, an important problem, because you can imagine that there are a lot of applications in which you not only need to depend on the value before you, but you need to depend in a lot of sequence, really. So you would like to have this receptive field very large in order to be able to capture these long-range dependencies. And the option number 1 would be simply to just say, okay, so the only thing that we need to do is consider large filters, but that's not really feasible from a practical perspective. Now, why is that? Because if you have, now we have, for example, here 2, a kernel size 2, that means that we need 2 weights in order to describe that. But if now we need 5, then we need 5 weights, and if we want 1,000, then we need 1,000 weights. Okay, so in that sense, it is not parameter efficient and also not really data efficient, because it is related to the amount of data that you will need, otherwise you are going to overfit. And here is an important, I want to accentuate why this is important. And to give an example, if you have a second of audio that is sampled at 22 kilohertz, which is not really high resolution, it's actually sort of crappy in a sense. You already require per second 22,000 points, which means that if we were to make filters in the way that we have just described, we will need per filter 22,000 weights per each of the filters. And of course, we don't learn just only one filter, but we learn a lot of these filters in parallel. And of course, we don't only just have one layer, but we have multiple of these layers. So you can directly see why this becomes a problem. So the question is now, what can we do about it? Are there other options that we can exploit in order to get these long receptive fields without a lot of parameters? And the answer is yes. And the way to achieve this is only to sort of stretch your convolutional kernel or dilate your convolutional kernel. So if you consider a dilation factor D, what you would do is you just take this convolutional kernel that you had, for example, with 2 positions, and you just stretch it by this dilation factor. Okay, so as a result, the receptive field that you now have is going to be also extended by this dilation factor. So if before we had a receptive field k minus 1, now we have a receptive field of D times k minus 1. And that's illustrated here. So before we had a filter that was like this, right? And now we stretch it by a dilation factor 4, which means we can now consider relations from 4 steps back in the past. Yeah, and an important point here is that since we still have the same number of weights, but we have not induced additional weights at all in the network. However, there is an important issue here, which you might already be thinking of, and is that we're actually inducing some sort of extreme sparsity to this filter. We are just saying here that the filter or the computation of this value is going to be depending only on the first and the last value within this receptive field, which means that if we want to compute values or consider values that are within these positions, that's just impossible with this formulation. And that's, of course, something that we would not like to have. So the solution in order to solve this problem so that we have long receptive fields in a dense manner, meaning taking into consideration all of the input values within the receptive fields, we can stack several convolutions on top of one another with different dilation factors. And by doing so, then we can construct something called a dilated causal convolutional network, or more often referred to as a temporal convolutional network, which looks as follows. So we have multiple layers here stacked on top of one another. And the first layer has a dilation factor of 1, the second one a dilation factor of 2, the third one a dilation factor of 4, and so forth. And if you see here in this picture, then we are really considering each of the values within the receptive field in order to do the computation. And this is obtained by having a exponentially growing receptive field. Okay, so if we see here, then we have an input of 16 values, and normally we will require 16 weights in order to be able to describe that with a normal convolution, right? And now we see that we have 2, 4, 6, and 8 weights, which means we are also only using half of the weights that we would require otherwise. So we have a, if we follow this dilation scheme that is shown here, and we denote the receptive field of the network by R, the total receptive field of such an architecture is given by 2 to the power of L, the number of layers, times K minus 1. And if you see, this is exactly the same formula as that we had before, just that we are replacing the D by the 2 to the power of L, and that's given because that's the receptive field of the opus, the layer on the top of all of the entire convolutional network, as is shown here. Which means that with this we can observe up to R minus 1 steps on the path. We consider, of course, always the point at the same location, and also since we have 16 voids, then we can look at 16. We are considering our receptive fields of size 16. We can also consider then 15 inputs in the past. Okay, let's now discuss some of the properties of these temporal convolutional networks. And the first and most important property, I would argue, is that the gradient flow direction of these convolutional networks is very different from those of recurrent networks. If you recall from earlier in this lecture, when if you were to consider this sequence here, this input sequence by a recurrent neural network, you would have to propagate or to unroll your network like this, sack over time, and then that means that you also will need to backpropagate over time, right? But now we are not considering such recurrencies at all here, and we are just sort of adding an extra dimension or looking at it from the top, which means that the gradient flow is not depending on the time anymore. That means that with this formulation, we are not using this backpropagation through time at all, and this has very, very important implications. The first one is that we now are able, because we are looking at the same sequence at the same time, we are now able to treat this in parallel, which means that we can, first of all, have much faster training than in RNNs or recurrent architectures, but also that we can use GPUs very optimal. And why is that? Because if you recall, when you do this unrolling and then you're doing the backpropagation through time, you first need to calculate the loss with regard to the last step, and then go sequentially back to the beginning in order to be able to train. And now we are seeing everything from, say, top, and then we can just in parallel do everything as it would normally happen in a convolutional neural network. So this is very important, but even more important than that, I would argue, is that we don't have the exploding or vanishing gradient problem anymore that we experienced before, right? What we saw in RNNs is that it becomes progressively difficult to learn from the past due to these recurrent connections that we have. But now, since we are getting rid of that thing, we don't have that problem anymore, right? Which means that as long as the input that is important or relevant or we want to learn from is within the receptive field of the network, then we are able to directly learn from it, regardless of how far in the path it is, okay? Of course, there is a catch here, and that's something that we're going to discuss later, and is that if the input is not considered by your receptive field, then you are not able to learn from it. So in comparison with the recurrent architectures, these TCNs bring these advantages. They are trained in parallel, and they do not exceed exploiting and vanishing gradients over the time axis. Hence, they can learn very easily from the far pass as long as it's captured by the receptive field. But this receptive field needs to be fixed a priori, which means that you cannot modify it while in the task at hand. So imagine that I'm talking and I just go into silence. Then the network will not be able to recognize it in the same way, because at a certain point, this silence is going to sort of disrupt the amount of information that it can get before the silence, okay? Even though the silence is not important for whatever I'm going to say next, let's say. Yeah, so that's a very important disadvantage. And also that, yeah, so since it needs to be defined a priori, you need to know what is the optimal value of this kernel size, but that's not an easy task. It can be dependent, or you don't really know right at the beginning, which makes it difficult. Yeah, and another disadvantage that you have is that even though you have this solution via the exponentially growing dilation factors, you are still adding parameters in order to consider it, right? You still need to add parameters in order to have a longer receptive field, and that's different from RNNs or recurrent architectures in general, because you have the same fixed parameter budget and you can just unroll it for arbitrarily long sequences. So it means that if you need to consider what kind of task you are going to solve in order to select for one or the other, but disadvantages of TCNs are quite important and quite interesting and worth exploring further. Okay, so we have seen this now, and now the question is, are they actually used in practice? And in fact, they are very broadly used in practice. We have applications in text, audio, time series, recognition, classification, generative modeling. Really, a lot of applications at the moment are based on these TCNs. And there have been several papers, for example, this from Bay et al. In 2018, that compare recurrent architecture with these TCNs. And what they show is that TCNs are very good, can really outperform the other functions, the other models, as long as the connections that you want to have fall within this receptive field. Yeah, so we see here tasks about just sequential modeling. So we have, for example, the sequential NIS, which is the NIS, the images. They are just sort of put into a string. They are just sort of flattened out. And the task is to predict whether that's a particular number. There are some other tasks here which are about music. And you are giving the network some, you can imagine of a piano, and you give as input the piano, the pieces that you are playing at a certain moment, and the network needs to predict the following one. So there are several tasks here where these recurrent networks were sort of the to-go solution. But we'll see here that actually TCNs can really outperform them without introduce or with the same number of parameters. So it's very encouraging and very cool to see. As a matter of fact, I think most of you have already got in contact with one of these networks. For example, each time that you say, okay, Google to your phone, the lady that answers you is actually this lady here. It's called a WaveNet, and it's based on a TCN architecture with some probabilistic interpretation of it, and it really works very well. It is really astonishingly good. And here I provide a link so that you can explore a little bit further some of the examples that they provide. It's really nice to see. It's really cool. And they can also use the same person to condition on different languages, for example, generate audio that is actually very, very good, very cohesive. Okay. So now we are going to delve a little bit longer into how to construct these temporal convolutional networks, because there are some important things worth noticing. The first one is that imagine that, okay, so as an example, imagine that we want to have a network that has a second of receptive field, which corresponds to 22,000 samples in a single second. Well, if we work out the math, then it would say to us that we would need for a kernel of size n, a network consisting of 12 layers. And that means that if we want to get something that has a higher receptive field, then we need to go even deeper, right? But as you saw in the video 4 of lecture 4, having very deep neural networks also can produce these vanishing gradients, which means that it makes training complicated. So if you don't remember this entirely, please go to the video 4 of the lecture 4 and refresh it a little bit. But what it boils down to is that we need to, in order to train these very deep TCNs, we need some tricks. And those tricks are the things that we are going to discuss next. So in order to avoid these vanishing gradients and improve learning, these TCNs actually use in practice a lot of tricks. They use batch normalization, they use residual connections, and optionally also dropout. You can look at video 4, lecture 4, in order to refresh this, but in a nutshell, the batch normalization sort of recenters the output of each of the layers. These residual connections make a direct connection within multiple layers at the neural network in order to improve the propagation of the gradients throughout the entire network. And dropout simply puts away some of the results or some of the hidden representation values in order to make the generalization of the network better. So it could be understood as having missing connections somewhere in the network and sort of creating additional connections in the network in order to aid for missing data or missing information in our samples. So what we have is that we have here a two layer neural network. So this is a convolutional neural network. Sorry. So this is a layer, and this is another layer, and a residual block. That's the name it's normally called. It's normally given to it. It's just computed as a two convolutional layer. So here you have the filters that are given by these connections, blue connections. So it's just a normal convolutional layer, a normal convolutional network of two layers, with the additional fact that you are just putting this value at the input and you're shortcutting it to the output via a sum. Okay, so that's also shown here. You have here the input, and you just have a direct connection to the output, and here in the middle you perform a two-layer transformation of the input. And here we see that this identity map that goes from layer L-2 to L is the residual connection. And yeah, as mentioned before, when you do the computation, then the gradient at this point is going to be sort of split within what is happening here and that will happen here, which means that the gradient is able to go back to the past easier. And of course, we can then have several of these blocks and then just stack them on top of one another. And then we can have very deep neural networks that incur less in these problems of the vanishing gradient. And they, in practice, show very good results regarding training and the time that you need to train them and so on. And the results, of course, the performance. Yeah, and as a final detail, we see here then that we are using a dilated convolution, that we use some sort of normalization, then the nonlinearity, and eventually a dropout function, but this is only optional. And we do two of these, we stack two of these layers together, and then we connect them with the input. Okay, so that's it. So in a summary, what we have seen here is that TCNs are a strong alternative to recurrent neural networks. They present some very important improvements, but also some very important limitations. We have seen that they are often used in practice. They indeed are a sort of the to-go solution in a lot of important applications, such as Google, the voice of Google, let's call it that way. Yeah, so far there are disadvantages and disadvantages. So when you have a given task, you need to look at these properties that they have in order to select the one that is best for you. But we think that TCNs have a lot of potential in making recurrent nets obsolete. And this is indeed something that we are exploring at the moment in my group. So we have a lot of follow-up projects in that part. If you're interested in working on this, you think this is interesting, please just ping me, and then we can discuss it further. And also, probably you have seen these transformer networks, this GTP3 and stuff like that. And TCNs seem to be a contender to them. And I call them here a lightweight contender because these transformer networks require a lot of memory, and that's why just on the OpenAI and Google and stuff like that really use them. And the rest of the people, we academia, for example, are not really able to have something like that. They use something like 500 GPUs to train and for 1 month and blah, 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 which is insanely much. So yeah. So these TCNs also give a alternative to these transformer networks for applications in which you don't have that lot of power. Okay, thank you very much for listening, and I hope this is clear for you. And if you have any questions, then just please let us know, and we are going to try to get back at you and solve them as fast as possible.